now, this is the title of my presentation. I am from the National School of Applied Sciences of Safi, from Cadi, Ayyad University of Morocco, North Africa. And the goal of my presentation is to make calculation of the electric field vector from the electric potential of uniformly charged ring at any point in space in cylindrical coordinate. The expressions of the components are obtained in terms of the complete elliptic integrals of the first, second, and third kernels. This is the setup. This is the ring, charged ring, and we want to find the electric field at the point P in the space. The X, Y, Z is the coordinate system. And the field, the expected expression of the field is here. It must be two components, the radial component and axial component. We start from the expression of the electric potential, which is here. And the R is the position vector, R, and the R is this position vector. And we make the decomposition, and we have this expression. And after we put this expression in this form, and we found this function of the electric potential. Here, key in this E is equal to 1 divided by 4 pi epsilon 0, where epsilon 0 is this constant. Since cos is a periodic function with period 2 pi and is in the additivity of the integrals, this function can be calculated only in the interval 0 pi as we can replace 2 pi by pi only because this condition. And the integration by substitution with this changement of the variable, and by substituting each variable in this function, we find this form. We can put mu equal a square 2, which equal this quantity. Can put for rho r here and q this in the denominator, and we put this quantity out, which this quantity is equal to q. And after this substitution, we found the potential function, which is in this form. Between 0, the integral will be calculated between 0 and pi divided by 2. Okay. And we found here the complete elliptic integral of the first kind, this expression, which is here. And we replace this expression by the complete elliptic integral of the first kind. We found the compact expression of the electric field, which is here. And now we will derive the electric field from the scalar potential, which is the scalar potential of uniform ring of Kerr. By using this relation, the null relation, the electric field equal minus gradient of the electric potential, or mathematically in this form. And the electric field is here equal to the gradient of the electric potential, and it means by expansion we find this expression. This is the axial component, and this the derivation applied to the potential function give us the radial component of the electric field. We must calculate this component and this component. We start with the axial. Derivation of the electric field from the scalar potential of the uniform ring of charge. We make some derivation. Yes, this is the partial derivation of the complete elliptic integral of the first kind. And after deriving, we obtain this function. Derive this, and we may make this derivation. This derivation is not here because we have derived this expression. We found this expression. And it is possible to show that this expression, after some manipulation, become in this form, where A is the complete elliptic integral of the second kind, and K here is the complete elliptic integral of the first kind. K is the minuscule K is the parameter. Deriving the axial component of the electric field vector from the gradient of the potential, we make this partial derivative, this derivation, and we put this parameter in the puzzle in the derivation of the potential like this, and we found this function because we replace K, this derivative, by its expression. And we have from here the axial component of the electric field, which is this, and we replace this quantity by this form. Finally we found the axial component of the electric field. This amount here, this function is now, this function is the complete elliptic integral of the third kind. And when the parameter n is equal to m is equal to k square 2, it becomes in this form, and it becomes in this compact form. We can replace this quantity by the complete elliptic integral of the third kind. And finally, we find the expression, the axial component of the electric field, which is here, okay? Where the A is the complete elliptic integral of the second kind. This expression is here. And the radial component of the electric field vector determination over another method is the direct method. And we'll make a hard calculation here. Take perhaps 14 page to make this by hand. And this is the plot of the elliptic integral of the second kind and the elliptic integral of the first kind. It diverge this, but this integral is converge, but this it diverge when the parameter k toward 1. And we make this calculation. We have the complete integral of the flow, the third kind, and the first kind, rho plus by the relation between the third kind and the second kind. Okay, and we found this expression. This is the radial expression of the electric field of the radial component of the electric field. And some limiting case and approximation in plane and on axis electric field vector, electric field determination in the plane of the uniform ring of charge. We have this component is equal to 0, and we have this form, this function, and we make some calculation in this expression, and we found finally that when z equals 0, we are in the plane, we have this expression, and we make some program in for example Mathematica like this, and we have the plot in the plane of the electric field in the plane of the ring. It converge, it diverge when k is equal 1 near the ring and the ring, but in the center of the ring, the electric field is equal to 0, and it become toward the infinity or at the vicinity of the ring, inside the ring, but here outside the ring. The electric field determination, the opposite axis of the uniform charge range. This is the noun expression. We can find this in the school, in the primary school, but not the university. But this form are in the university, for example. And the conclusion, we have determined the axial component of the electric field vector. Here it is. And the radial component is here. So this expression. And the orthoradial or azimuthal component is 0, is equal 0. For our purpose, the cylindrical coordinate was selected to resolve the problem. I thought it is possible to work in the Cartesian or spherical coordinate system as well. We can repeat this demonstration in this system of coordinates. Thank you very much.
Thank you.
Okay. There is question. There's questions. This is the physics. There is questions. Dr. Olga Estrango, there is questions.
Actually, I have one question. Please show first slide.
First slide, okay. First slide. This?
No, there is
This?
vector. No, next, yeah.
This, okay.
Yes. You mentioned that you used cylindrical coordinates.
Yes, cylindrical coordinate, yes.
Not spherical coordinates. Why?
We can do this calculation but we'll do it. It must give this another form
Mhm.
of the function. But if we plot this form in the graphic, we must find the same plot. We will find another expression, another form.
Mhm.
Yes. Because the coordinate, the spherical coordinate is different, is different from the cylindrical coordinate
Yes. Yes.
and the Cartesian coordinate. But we
Mhm.
must find the three expressions which are different. But the calculation of the value, will be the same. It must
Mm.
be the same value at each point in space.
Okay, because I guess for with big P point, there is
Because P is
more possibilities because for spherical coordinates this radius is the same and this point should
the
be
same.
with
The
the
point,
same distance. Yeah. Mhm.
and physically, the calculation of the value of the electric field will be the same
Mhm.
independently of the system of the coordinate which you use.
Mhm. Mhm.
Because the value is the same, because the range is the same. But the expressions in three systems of coordinate will be different, but the value will be
Mhm.
the same.
Mhm. Mhm. Yeah,
Yes.
most possibilities. Yes, thank you, Professor.
Welcome. Is there another question?